In the last video, we saw the working of the Deutsch algorithm to solve the given problem. Now, if we generalize the problem for n qubits, that is, f of x is a function that takes n qubit inputs and gives single bit output, and we have to check whether f of x is constant or balanced only with a single evaluation. This generalized problem can be solved using the Deutsch-Jozsa algorithm. We'll use this quantum circuit to solve the given problem. So from the given circuit, the upper entry called as the query register is the n qubit 0 state, and the lower entry called as the answer register is the 1 state. And as usual, this circuit is divided into 4 states of psi 0, psi 1, psi 2 and psi 3. So now let's try to get each of these states. So psi 0 will be equal to the tensor product of 0 tensor n state and 1 state, which is given as 0 tensor n into 1. Now the 0 tensor n state is operated by n qubit Hadamard transform, and the 1 state is operated by a single Hadamard transform. Therefore psi 1 will be equal to h tensor product n 0 tensor product n tensor product h operating on 1. Now this operation can be written as h tensor product n operating on 0 tensor product n equal to 1 by root 2 raised to n summation x for all 0 1 bits raised to n into x. So to check this operation, let's see a few examples. So we have for n equal to 1, h operates on a single 0 state, which gives us 0 plus 1 by root, which is our plus state. Similarly, for n equal to 2, h operates on 2 0 states, which can be given as this equation, and when further multiplying it, we'll get this equation. And if we simplify it further by taking the sum over all the values of x, for x being 0 and 1, we'll have this general equation. So similarly, for n qubits, h tensor product n operating on 0 tensor product n state will be equal to 1 by root under 2 raised to n summation x belonging to 0 1 for n bit string summing over all values of x. So we got this value for psi 1, and we know h operating on one state gives us 0 minus 1 by root 2. So finally psi 1 will be equal to 1 by root 2 raised to n summation x belonging to 0 1 raised to n summing over all values of x into 0 minus 1 by root. Now to get psi 2, we need to apply the oracle gate, that is the UF transform on psi 1, which implies psi 2 will be equal to UF operating on psi 1, which is equal to UF. Our psi 1 was 1 by under root 2 raised to n summation x state into 0 minus 1 by root 2 the whole bracket. And since all our operators are linear, we take UF inside the summation, which gives psi 2 equal to 1 by 2 raised to n summation x u of f operating on x and 0 minus 1 by root 2. Now we know the operation of u of f on two states x and y gives us x into y XOR f of x. Therefore psi 2 will be equal to 1 by 2 raised to n, and this root 2 will also come out, summation u of f operating on x and 0 minus u of f operating on x and 1, which would be equal to, using this transform, x 0 XOR f of x minus x 1 XOR f of x. Here our y was 0 and here our y was 1 from the general equation. Now we know for all values of f of x, 0 XOR f of x will ultimately give us f of x, which implies psi 2 will be equal to f of x, taking the x common outside, minus 1 XOR f of x. Now for this state, there could be two possible values, which can be written as 0 minus 1 for all f of x equal to 0. That is, if this is 0 and this is 1 XOR 0, which will be 1, which will give us 0 minus 1, and minus of 0 minus 1 for all f of x equal to 1. That is, this would be 1 and this would be 1 XOR 1, which would be 0, and flipping it will get a negative sign. So instead of writing these two states for two conditions, we can simplify this as minus 1 raised to f of x into 0 minus 1, which implies our psi 2 can be written as, taking this value of this whole function state, we get this expression for psi2, where I have taken 1 by root 2 inside this state, which is our minus state. Now after getting psi2, the first qubit of psi2 is operated by n qubit Hadamard transform. That is, our first qubit is operated by H tensor product n transform. So in a nutshell, if we ignore this constant and summation, this transform is operated on the x state, which implies H tensor product n is operated on x state. Now we saw that H tensor product n operating on 0 tensor product n gives us this expression. In a same manner, H tensor product n operating on x will give us this expression. So now let's stop thinking about our problem and let's try to evaluate this particular operation for a while. So in order to derive this expression, we have H operating on xi state, where xi is a bit string for 0 and 1 value. This is equal to 1 by root 2 0 plus minus 1 raised to xi into 1. We can check this condition for x equal to 0 and x equal to 1, which implies for x equal to 0, h of 0 is 1 by root 2 0 plus minus 1 raised to 0 into 1, which gives us our plus state. And similarly, when x is equal to 1, h of 1 gives us the minus state. So this proves the validity of this expression. So let's take x as a 2-bit string, that is x0 and x1, which implies n is equal to 2. So when H tensor 2 operates on x state, which is equal to H tensor 2 x0 x1, we have H operating on x0 and H operating on x1. There is a tensor product, and from this general equation we can write H of 0 as 1 by root 2 0 plus minus 1 x raised to 0 into 1, and h of x1 as 1 by root 2 0 plus minus 1 x1 1. Now taking root 2 common, we have 1 by root 2 square, and multiplying the individual state, we'll have 0 0 will give us 0 0, and 0 minus 1 x1 1 will give us minus 1 raised to x1 0 1. Similarly, we'll have minus 1 raised to x0 1 0 plus minus 1 raised to x0 plus x1 1 1. Now for the state x0 x1, which could be 0 1 or 1 0. Now 0 1 implies that this can be written as minus 1 raised to x1, and 1 0 implies that could be written as minus 1 raised to x0. That means this power of x implies the position of 1 in the qubit state. As you can see, for both the values of 1, we have x0 also and x1 also. For 1 on the first position, we have x0. I hope you are getting this. So we can write these powers of minus 1 in a more general way, that is, and since there is no power of 1 here, we can write minus 1 x dot 0, which would be 0, which will result in 1 here. Similarly, x1 can be written as minus 1 x dot 0 1 0 1 plus minus 1 x raised to 0 can be written as x dot 1 0 into 1 0 plus x0 plus x1 can be written as minus 1 x dot 1 1 1 1. Now these are the dot product operations. For example, x dot 1 0 is x0 into 1 plus x1 into 0, which would be equal to x0. Therefore, x0 can be written as x dot 10. I hope you got this general way of writing this expression. So now let's represent all this state of 0 0 0 1 1 0 1 1 and this dot products of zeros and 1 with a variable z, which is also a 2-bit string for zeros and 1. So this expression can be further written as h tensor product 2 into x will be equal to 1 by root under 2 square. Since 0 state had no coefficient, we'll leave it, plus minus 1 x dot z 0 1 plus minus 1 x dot z 1 0 plus minus 1 x dot z 1 1. This can be further simplified by taking the summation over z, which would be equal to 1 by root under 2 square summation z belonging to 0 1 bit string for 2 bits minus 1 raised to x dot z into z state. So for h tensor product 2 operating on x state, we got this expression. So similarly, h tensor product n operating on x state will give us 1 by root 2 raised to n summation z for n bits minus 1 raised to x dot z into z. So now I hope you understood how h tensor product product n operating on x gives us this expression. So when h tensor product n will operate on the first qubit, so the final expression for psi3 is given by this expression. Now if we take summations one side and simplify it further, we can get psi3 equal to this expression, where 1 by root under 2 raised to n and 1 by root under 2 raised to n would give us 2 raised to n. And since we don't need the second qubit state 0 minus 1 by root 2, we shall ignore it for our further purposes. Now let's take the amplitude for the state 0 tensor product n. Since z represents all the states, z can be 0 0 0 plus 0 0 1, like this, all the states for our n qubits. So we will take only the first state, that is 0 tensor product n. So to calculate the amplitude of this state, we'll have z as 0 0, which is essentially this state only, and x dot z equal to x dot 0, since z is 0, which would give us 0. So the amplitude of 0 state tensor product n will be summation x minus 1 raised to f of x divided by 2 raised to n. Now if f of x is 0 for all values of x, then the amplitude of 0 tensor product n state will be 1 by 2 raised to n summation x minus 1 raised to 0. Now minus 1 raised to 0 summing over all the 2 raised to n values will give us 1 by 2 raised to n, 1 plus till 2 raised to n ones, right? So this can be written as 1 by 2 raised to n, and this summation will be 2 raised to n. 2 raised to n, 2 raised to n cancels, which gives us 1. So if f of x is constant, that is 0 for all values of x, we get 1. Similarly, if f of x is constant and has the value 1 for all values of x, 1 by 2 raised to n summation x minus 1 raised to 1 would be 1 by 2 raised to n with a negative sign summing all the values of 1, which would give us minus 1 divided by 2 raised to n into 2 raised to n, which would be minus 1, which implies for all constant values of f of x, which can be either 0 or 1, the amplitude of 0 tensor product n state will be plus or minus 1. Similarly, if f of x is balanced, that is for half the value of x, f of x is 1, and for the remaining half, f of x is 0, we'll have the amplitude of 0 tensor product n state as 1 by 2 raised to n, 1 minus 1 plus 1 minus 1, like this till the 2 raised to nth term. So all these terms, since they are even, they'll cancel out each other, which implies if f of x is balanced, the amplitude of this state would be 0. Now we know probability is the square of the amplitude, which implies if f of x is constant, the probability of getting 0 tensor product 1 state is 1, and if f of x is balanced, the probability of getting this state is 0. That means that if our function is constant, there is a 100% probability of getting the state after a measurement, and if a function is balanced, there is a 0% probability of getting this state. That means the state doesn't exist. So if you took the measurement of the first qubit of psi3 state and we get 0 tensor product n state, that means our f of x is constant, and if we get any other state except this state, then f of x is balanced. So this was in a nutshell our Deutsch-Jozsa algorithm. So with the help of the Deutsch-Jozsa algorithm, we were able to find out whether a function which had a n-bit domain is constant or balanced only by taking a single measurement.